Hello participants, I invite you to lecture 42 of micro irrigation engineering course. Lecture 42 is on performance evaluation of a sprinkler irrigation system component. System component here, one of the component which I am considering is sprinkler head. Any system or particularly with respect to sprinkler irrigation system, we are interested to evaluate its performance so that system can be installed and it can work as per the desired capacity. So, this particular component whether it is working satisfactorily, and this is one aspect to evaluate satisfactory working of sprinkler component. Another one is to design the system as it is behaving, as it is performing in the field, accordingly operating pressures, the spacing between the sprinklers, application rate of the sprinkler nozzle, that can be decided and it can be operated. So, mainly in this particular topic we are going to cover the evaluation of sprinkler parameters, and we will work out the data collected from the field, how the various evaluation parameter, performance parameter, it can be estimated. When we talk of performance of a sprinkler nozzle, so sprinkler nozzle, when we say a nozzle is evaluated for its application rate and its suitability with respect to the infiltration capacity of the soil. So, primary factors are important parameters we can say which influence its operation. One is operating pressure and another one is nozzle geometry. These two actually are the important factors that affect the water application rate. When we say and how much is the discharge which is coming out of the sprinkler, that will depend upon the operating pressure. Nozzle geometry, I mean to say what is the diameter of nozzle opening, what is the shape, whether it is a circular shape, whether it is a rectangular shape nozzle or it is the square shape nozzle. So, water emerging out of the sprinkler nozzle, it is going to be influenced by the shape of the nozzle opening, and then angle, at what angle of throw the jet which is emerging out of the sprinkler nozzle, at what angle it is emerging. So, how the particular nozzle angle is fixed at the time of manufacturing. Now, the parameters which are evaluated for any sprinkler irrigation system, it is evaluated based on the what is the discharge from a sprinkler, what is the how much distance it is throwing, how the sprinkler nozzle it is distributing the jet when it is getting broken, and then how its movement takes place, how the distribution takes place, what is the size of the droplet, how much is the application rate for a given pressure, and then we want to evaluate how uniform water it has been sprinkling or distributing out of the sprinkler nozzle. So, how it is uniformly distributing the water droplets which are falling, is it. So, there is one specific index which has been prepared, that is uniformity coefficient. Discharge from a sprinkler, it is a function of the diameter of the nozzle and operating pressure. These two are the important thing, and C is the coefficient of discharge. The discharge from a sprinkler nozzle, it is normally the sprinkler nozzle geometry, it is circular in shape, and it is so it looks like an orifice, and then it is a orifice flow. So, x value of x is the approximately equal to 0.5. I, which here it is given, that is the number of sprinkler nozzles or sprinkler head, that I varies from 1 to n. So, total discharge from a system, it is estimated by using this expression, where k is the constant that depends on how many number of sprinklers it has been used, and of course, the another one is that what is the unit which we are giving. If it is say in we are putting it in centimeter or millimeter, or if we are putting here it is in also in kilopascal. So, accordingly the values, the unit will be, the value of k will change, and also the discharge can be expressed in meter cube per second, liter per second. Normally, these two units we are using. This is a one particular company, the pressure discharge relationship. So, here when we are giving a pressure from a sprinkler nozzle, which is expressed in pound per square inch, and these are the two diameters. One diameter is your range nozzle. The diameter of the range nozzle is 3 by 32 inch and 6 by 64. 6 by 64 is this is the spreader nozzle. So, when say particularly this nozzle, there are twin nozzle system, and this twin nozzle, when suppose it is operating at 25 psi, that is 25 per pounds per square inch, it will deliver 1.2 gallon per minute is the discharge. So, like this for different pressures, the discharge table, it is supplied by the manufacturer, it is available, or else one can calculate the value of the discharge. Now, distance of throw, this is one parameter which I told, the distance of flow, it governs the spacing between the adjacent sprinkler, means we will distance of throw will depend upon the pressure. More the pressure, more will be the distance of throw. So, and then we want to have the better or uniform coverage of the the sprinkler jet which is coming out of this. So, we will decide what should be the spacing between the sprinkler nozzles along the main as well as along the lateral. So, that way it is decided. Normally, the distance of throw, it is published by the manufacturer, and the manufacturer gives the leaflet where operating pressure, what is the diameter of the nozzle for a given diameter, how much is the distance of throw for different operating pressures and nozzle sizes. So, those informations are available. Distribution pattern, how the water is being distributed. So, distribution pattern will depend, again I am telling you, that will depend upon the operating pressure, nozzle geometry, wind speed, etc. There are several things which are influencing the distribution pattern. A wide range of droplets caused by the higher pressure operating pressure results in triangular shape distribution pattern in which the depth of application increases linearly from the outer edge of the pattern towards a sprinkler. Varying means nozzle angle affect the pattern, that is weighted area, and then the means that in the pattern shape. Now, here what we are seeing the how the distribution pattern, I was telling you that how the I mean when there are different operating pressure. So, when the pressure applied is low. So, you see here that when the sprinkler is at this particular point and then water is distributed. So, some places it is more a larger depth and then means immediately adjacent to the sprinkler. 0 refers to the sprinkler head is at this place, and then the either side of the sprinkler means it is on either side what you find that the water is being distributed by the sprinkler head which is located here, and is this side as well as this side you find a symmetry. So, water distribution, but the here depth of water is more, it is low. So, this is why it is so, because of the low pressure. When optimum pressure is given or ideal pressure is maintained, you will find this is a typical water distribution pattern from a sprinkler. So, more is the depth of water at the center or where the sprinkler nozzle is available, because spreader nozzle it is distributing more amount of water nearer to the sprinkler, and as we go farther from the sprinkler on either side. So, we find that this is the depth of water is less, it is reducing, but this is the ideal and we are required to give appropriate overlap, so that the uniform depth of water can be maintained. Here in this case, when pressure is very high, when the pressure is very high, you find that the this type of shape it maintains. So, the distribution of water, ideal distribution of water is this one when the optimum pressure is maintained. Droplet size also it is influenced by the operating pressure, and it affects the when the droplet size is large, what happened, it causes the impact on the ground surface, means water droplets which resembles like rainfall. When the droplet size is more, what will happen, it will restrict or it will make the formation of seal. So, it will have a sealing effect, and that will cause the higher runoff as well as the soil erosion will take place. So, nozzle opening shape, operating pressure, that is going to affect the droplet size as compared to nozzle angle. Application rate from a sprinkler nozzle, it should be such that it does not form runoff. It should be such that it should be less than the infiltration capacity of the soil. The average application rate of individual sprinkler is given by I is the rate of application or precipitation intensity, you can say, is equal to Q by A. If we are expressing Q in liter per second and area weighted by an sprinkler it is in square meter, then we need to multiply it by 360 to take care of the unit constant. When there are several identical sprinklers, they are placed in a field, and then the sprinklers are having this, it could be a square pattern, it could be an rectangular pattern, that is L by say L is, suppose L is larger than the S, okay, then it is going to be the rectangular pattern. If L equal to S, then it becomes a square pattern. Now, application rate, when there are several identical sprinklers are in operation, then one can find out what is the application rate. So, Q by A, this is what this is only A is replaced by L into S. What is L? L is the distance between the sprinklers along the lateral. S is the distance between the sprinklers along the main. So, application rate is estimated like this. Higher the application rate, more will be the runoff, poor water distribution and loss of water is going to take place. The another important parameter of evaluation which is important, that is uniformity coefficient. It is an index to measure uniform depth of water application, and it is affected by the what is the pressure, what is the size of the nozzle, and what is the spacing between the sprinkler it has been kept, and whether there is a ideal wind condition, calm wind condition exists, or if there is a more wind speed. So, it may cause the drift, wind may cause the drift in the water distribution pattern. So, we need to take care while we are deciding the spacing between the sprinkler depending on the depending upon the application rate, depending on the your operating pressure. So, that is going to make the difference in the value of uniformity coefficient. Now, in order to estimate the uniformity coefficient, it is the Christiansen in 1942, he gave the expression, and this expression is still valid. So, this is an important parameter to evaluate the sprinkler uniformity coefficient. What is sprinkler uniformity coefficient? It is given by Cu equal to 100 multiplied by 1 minus summation, the summation, that is the numerical deviation of the individual observation from the average application rate. So, we will say, suppose we have got 15 number of sprinkler depth of observation. So, what we will find out 50 from the 15 your depth of sprinkler observation that has been collected. So, what we will first find out the numerical your average, arithmetic average of these values. So, 15 values divided number of sum of the depth divided by number of observation, that will give you the average value of all the observation. Now, from there actually whatever average we have got, so individual values. So, x I, that is x 1 minus m will be the one value, that is one deviation. Then another deviation will be x I, that is x 2 minus m, x 3 minus 1, like this x 15 minus m, and then we will take the difference value, sum of deviation, that value, and then that is taken as a absolute value. So, those sums will be used to find out the numerical deviation, and that is divided by m into n. This will, if we find from the observation it is equal to 85% or more than 85%, it is considered satisfactory, and if it is more than 90%, then it comes under very good performance. Now, the various parameters which are used to evaluate a sprinkler system, that for a given operating pressure, what is the discharge coming out of the sprinkler. So, this is given by Q equal to C into A into root TGS. What is C? C is the coefficient of discharge, which is a function of friction as well as contraction losses. A is the area of cross section of the sprinkler nozzle. If it is circular, then we can simply write pi d square by 4. H is the operating pressure. Okay, this if you are expressing everything in meter, means your A in if you are expressing in square meter, and then if you are putting H is in meter, then the corresponding discharge will be in meter cube per second. Now, water spread area of the sprinkler. So, when sprinkler is being operated, so once it is operated, it gets the stable value. one need to find out what is the radius of coverage. So, this radius of coverage, this particular radius of coverage or weighted area, this is R, that is given by capital R, and so water spread area of the sprinkler is given by pi into R square. Now, this R, this R is nothing but the radius of weighted area that has been given by the Kawaja and Pillsbury 1986. They got a they have got the empirical relationship, and that empirical relationship has been used, and d is the diameter of the sprinkler nozzle. Now, the another parameter one can evaluate, that is the breakup jet index. Breakup jet index means basically it is giving that at a given operating pressure, when the sprinkler nozzle the particular jet it appears. So, it hits on the arm, and that hitting on the spring arm which deflects. So, there is a particular it guides the water to flow through, that is a smooth, but it hits, and that start the breakup jet droplets. So, those droplets breakup jet is evaluated by this expression, that is a P d equal to H divided by 10 q to the power 0.4. So, H is the operating pressure, q is the discharge in liter per second. See, this q is a capital Q, which is means expressed in cubic meter per second. Here this q is also in the discharge form, and then it is given by liter per second. Now, the values of P d, because H if you know and Q you know, then you can find out what is the P d. Now, if P d, that is a breakup jet by jet index, is given by P d, if it is greater than 2, that condition of the drop size is good, means it is acceptable, it is a good. If it is a P d equal to 4, the condition of the droplet size is waste, and then if the P d is greater than 4, then pressure is being wasted, means electricity or any energy which we are using for operating the sprinkler, we are wasting the energy, because the operating pressure it is at the higher side. The other part of evaluation is uniformity of application. So, this part already I have told you. Now, we will just to demonstrate you how the observations which parameter which I have told, how they are to be determined, how to find out the emission uniformity, how the data should be collected. So, this I am just giving you experimental procedure, and then we will operate one sprinkler head in the field, that you will also study and learn from that. We want to perform evaluation test. So, sprinkler system should be installed at a desired location in the field. Note down the specification of the pump coupled with electric motor. Observation on the wind, means that is a climatic observation we need to collect for taking the observation. With respect to sprinkler system, and we want to find out what is the capacity of the sprinkler system, what is the discharge of sprinkler system. So, we need to really conduct the test. So, first of all we will be dividing the whole field in square grids, and then in the center of each grid, at the center of each grid one plastic can will be kept. And then what happened, if the normally these cans should be placed 2 meter apart for a smaller spacing emitters or drippers or sprinklers, whatever we say. So, means for a smaller set, that 2 meter apart it should be done when the spacing is 10 meter apart. 3 meter when we are putting, it is for the larger spacing sprinklers, means when we have got larger farm area, then we want to operate all the sprinklers at a stretch. In that case, the such provision should be there, and if it is for a larger spacing. the grid can be should cover the entire area of the sprinkler head. Yeah, theoretically it should be, otherwise if there is no wind condition exist, this is done for the entire area. When there is a wind or some kind of field is going, means the data are going to be the affected. So, it can be also done that we are taking half or 1/4 of the field, 1/4 of the circular field, because the sprinkler rotates. So, it makes one particular circle, that is a 360 degrees. Now, if you are putting a particular angle that up to 90 degree, up to 180 degree, we should evaluate. So, then procedure remains same, procedure will remain same, types of the data will remain same, only thing you will be getting the number of observation will be different, number of observation will be half. Why we can do in the half? We assume that this, if it is in a the ideal condition. So, whatever data we are collecting, such data will be replicated in the other side. So, can grid should be, means it should be covered entire area. We will note down the observation of the range as well as the sprinkler nozzle size, their sizes, operating pressure, and then corresponding discharges. That relationship already you have studied, that Q equal to C into A into root 2 GH. So, operating pressure and discharge relationship is required. Pressure is measured by using pressure gauge, which is fixed on the riser pipeline, or using a pitot tube also. The pressure, these data are collected, that is a pressure and discharge data can be collected. Now, discharge is measured by connecting the physical tube on both the nozzles, which is sprinkler measure range nozzle as well as the sprinkler spread nozzle. So, this data which we are connecting with the help of tube, the discharge is collected in a can, and then for a given period, then we will convert in the discharge, means precipitation intensity form, that how much is the amount of water it has come out. So, either we can say in the volumetric form or in the depth wise form also it can be converted, and then one can know what is the precipitation intensity. Like this, we will collect the observation on radius and water spread area, and then we will repeat the observation for the different pressures to achieve desired uniformity coefficient of 85% or more. So, we need to operate for the other pressure till we are not getting the coefficient of uniformity more than 85%. Now, so these are the observations which we will be collecting. The observations on the pressure of the water at the nozzle, the discharge of smaller nozzle, discharge from the large nozzle, diameter of small nozzle, diameter of large nozzle. These diameters are used to calculate the discharge from the smaller nozzle as well as the larger nozzle. So, this is a measurement we have done. Wind speed is measured by using the anemometer, and then wind direction. So, we will note down what is the wind direction, and then the temperature, what is the ambient temperature, relative humidity, pump size in HP, what is the inlet diameter of the pump, what is outlet diameter of the pump, the discharge from the pump. All these data are useful, and that this can be given. So, like this, for serial number 1 means basically it is the row and column at the center of these row and column, that particular location, one can be kept and observation can be obtained. So, O1, O2, O3 are the lines on where the cans are placed, and O is the center of sprinkler over which the sprinkler head is kept. So, after getting those data, as I told you that we will find out the x I minus x bar, sum of x I minus x bar, that so this sum will come total of all the values, and then one can calculate what is the emission uniformity. Now, we are conducting a test in the field. Here we are demonstrating you a sprinkler irrigation system. So, sprinkler irrigation system
also uses a pump which creates adequate amount of pressure. So, water is being lifted from the source. Since it is a demonstration unit and used for testing a sprinkler nozzle. So, here it is a small tank where the water is stored, and then there is a pump. You can see here at this place there is a pump, and this pump is coupled with an electric motor. Now, the suction end of the pump, there is a flexible pipeline where the water is being taken. The lower end of the pipeline of the suction pipeline, there is a footwall. So, footwall is the purpose of footwall is to retain water. So, first the suction pipeline, it is filled up with water up to the filling the impeller, so that it does not take air, whatever air available in the pipeline, it will be removed when it is filled up with the water, and then water is means it is used for priming. It is used for priming. So, a footwall you can see here at this end there is a flap, it has come out, and when we are filling water, then this particular wall it gets closed. That this is the purpose of footwall. Then the water is taken. This is the delivery end of the pump which is connected, and then it goes to the main pipeline, and at appropriate location sprinklers are attached. We have taken water from the delivery end of the pipeline. So, a main pipeline of adequate diameter. Normally, these pipelines are of 2 inch, 2.5 inch or 3 inch in diameter, and each pipeline is of 3 meter, 6 meter or 9 meter long. So, here we have taken water from the main pipeline, and then with the help of a 90-degree bend, a lateral pipeline had been joined. Now, as I told you that there is a coupler at appropriate location. Coupler is used to attach sprinkler at a place where we want to give irrigation. So, this is one coupler in which one lateral pipeline will be attached with the another lateral pipeline, and on this coupler you can see here that on this coupler there is a riser pipeline which is of 1 inch diameter, 1 meter long, and this end is connected with a pressure gauge. Pressure gauge is connected here to know what is the operating pressure of a sprinkler head. Now, a sprinkler head, here you are seeing this is a sprinkler head which is made up of an alloy, where there are 2 nozzles. These 2 nozzles are discharging at given pressure, and one nozzle is a range nozzle, another this particular nozzle is a range nozzle, the other nozzle is a spreader nozzle. This is the counterweight, and here there is a spring. So, when water it comes, the spring compresses and then a torque is created. So, because of this torque, when the jet will come, it will hit. So, once it is hitting, then it deflects, and deflection it causes the sprinkler head to rotate. So, this way it takes the one particular circle. Now, we will be monitoring the pressure at a given pressure, how much is the discharge coming out of the sprinkler. So, there is a relationship which I have already explained you, that discharge from a sprinkler nozzle is directly related with the operating pressure, which is square root of the operating pressure. So, we will find out what is the total discharge, mean discharge from this nozzle plus discharge from this nozzle, both the nozzles will be operated to know that how much discharge we are getting at a given pressure. From that data we will also find out the coefficient of discharge from these two sprinkler, because we know the pressure, we know the discharge. So, and we know the operating pressure, we know the discharge, we know the value of G. So, we can find out the coefficient of discharge. In order to measure the discharge from both the nozzles, two pipelines which were fitted with the nozzles. Now, the total volume of water, it is being collected in 10 seconds, and then we will find out the volume of water collected in 10 seconds will give the discharge at 1 kg per square centimeter. Yes. This is the discharge from another nozzle. So, individual discharges we have collected in 10 seconds, and then we will, using this data, we will find out the coefficient discharge for each nozzle, that is a range nozzle as well as spreader nozzle. Now, we can see that in how much time it takes to take one round. So, the sprinkler revolution in per minute, it can be found out. So, this is one observation it is to be used. The another observation what you see, there are measuring cans. So, depth of water which is collected in a given time, this depth of water will be used to find out the uniformity of water distribution. Another observation which you can see here, what is the diameter of coverage. So, diameter of, this is the radius, it is being measured, that how much is the wetting radius from the nozzle, which is when the nozzle sprinkler nozzle, it is operating at 1 kg per square centimeter. So, we are measuring operating pressure, we are measuring the volume of water, then discharge, then we are measuring what is the diameter of coverage of wetting diameter, we are measuring the depth of water collected in the cans. These depth of water collected in each can is used to find out coefficient of uniformity, that formula which already I have explained in theory class, and we have worked out problem in the tutorials.
Now, this sprinkler problem, basically a numerical example, it has been given where one can evaluate emission uniformity, one can evaluate the pattern efficiency. So, from a one particular sprinkler which is placed over here, this is in another corner, another sprinkler is placed, this is in the this corner, there is a one sprinkler has been head has been placed, and at this. So, this particular sprinkler system is kept in at a appropriate locations, and then at the center of each grid these data have been collected. These data can be in milliliter, or simply one can say that these data are in millimeter depth of water which is collected in a can. So, volumetric form, or it can be in the depth form, these data can be collected. So, in this particular problem, sprinkler heads which has been used, these sprinkler heads, the one particular observation is 4.365 into 2.381 millimeter. So, this is one the range nozzle diameter, this is the spreader nozzle diameter which is operating at 2.8 kg per square centimeter. So, now area is given, sprinkler diameter is given, one can find out the what will be the operating pressure, theoretically what will be the operating pressure. So, area one can calculate, we have been given the operating pressure. So, Q equal to C A root 2 G H, the value of C, it is ranging from 0.995 to 0.98. So, you can substitute the value and you can find out how much is the discharge for at 2.8 kg per centimeter square. Now, the other data which are available, wind speed is given 3.5 kilometer per hour, and this is from the southwest side, relative humidity is 42%, test of time is 1 hour. So, these data are were collected from the field, and from these data we want to evaluate the coefficient of uniformity. So, these data we have kept in the descending order of the magnitude, means the highest value is 10.2 and there is one observation, there is only one observation of 10.2. Now, you can see 9.9 is the another value, this has also only one time it has occurred, but 9.4 millimeter or 9.4 milliliter of water, it has been obtained from 2 cans. So, like this, if you see here the highest depth of water which is 10.2 and the lowest is 6.6, and then the how many times these observations. So, there were 21 number of observations, 21 number of observation, and then what we are doing, we are multiplying with the means application rate multiplied by the frequency. So, this is the observation multiplied by the frequency. So, this is the means that it rather it is the depth of water application. So, this depth multiplied by frequency, and then you are summing the value, that is m into n, it is coming as a m is the average value multiplied by number of observations. So, number of observation is nothing but frequency. So, this value is the depth of application multiplied by the faculty. So, m into n equal to 178. Numerical deviation, taking the observation. So, numerical deviation from the first observation, that is 1.6, we will be getting the value of the frequency into deviation. So, this is coming as a summation of x that is your deviation from the mean is 17.4. So, we are getting the mean value, that is m, mean m equal to sum of all the observation divided by number of observations. So, sum of all observation is nothing but the previous value, that is your depth of application multiplied by the frequency number of observations. So, this is 178 divided by 21 is 8.48 millimeter or ml, whatever the unit which we can use. So, this is the value, and then we will work out the emission uniformity. So, emission uniformity is given by 100 into 1 minus summation x, that is the deviation from the mean summation value divided by m into n. M is the number of average value, n is the number of observations. So, when we multiply we get this value, and then we found that the computed value of Cu from the data is 90.23%. It is highly satisfactory, and then this particular setup of the pressure is giving best performance. Pattern efficiency is given by minimum depth divided by mean. So, minimum depth, if you remember, it was 6.6 millimeter and 8.48 is the mean. So, we are getting 77.83% is the pattern efficiency. This is also a very good indicator that this particular sprinkler system which we have is taken from the field data, it is giving very good performance from the operational point of view. Now, let us summarize this lecture. So, here we have got evaluated the different parameters which are the sprinkler head, discharge relationship. We have evaluated how the water distribution takes place, water distribution in the form of emission uniformity. We also worked out one example to make you more clearer about the how to find out the uniformity coefficient, how to find out the pattern efficiency. So, you learnt about this, and in forthcoming lecture we will work out numerical examples on sprinkler irrigation system. So, and for this particular topic you may refer these books on this topic. So, thank you very much.